Today we'll discuss about how to calculate post-test probability based on likelihood ratios. Suppose you go to a town where it has been snowing for last 3 to 4 days. Now you are worried about next week. Somebody tell you that it snows here for 3 to 4 days every 1 to 2 weeks. As now we have information on pattern of snowfall in that town, based on these information, we can calculate the probability of snowfall during next week. Such calculations are based on principles of Bayes' theorem. According to this theorem, we can calculate the probability of event if we have some information or conditions related to that event. Like in this case, we can calculate the probability of snowfall during next week based on patterns of snowfall in past. Similarly, if we know the pretest probability of a disease, with the help of information from diagnostic tests, we can calculate the post-test probability of disease. In general, we estimate pretest probability first, then we calculate the likelihood ratios with the help of sensitivity and specificity of test. By multiplying these two variables, we can calculate the post-test probability of disease. So we have three components of this formula. One is pretest probability, one is likelihood ratios, and post-test probability. We'll discuss all these components in detail. We can see in actual formula, it's the pretest odds, and multiplying it with likelihood ratios, we get the post-test odds. So in first step, we need to convert pretest probability to pretest odds. And when we get results in post-test odds, we again convert post-test odds to post-test probability of disease. First of all, let's discuss about pretest probability. This is probability of presence of disease before a diagnostic test is performed. Prevalence of disease, history, physical examination, and results of previous diagnostic tests help us in estimation of pretest probability. Similarly, there are some typical signs and symptoms that strongly suggest presence or absence of a particular disease, like presence of guarding and rigidity on abdominal examination suggest high probability of peritonitis. Based on these information, we can estimate probability of disease from unlikely to very likely. We also have some scoring systems available, like for DVT and pulmonary embolism. And based on these scoring systems, we can calculate exact percentage of pretest probability. In this diagram, we can see threshold points at different levels of pretest probability. A testing threshold, suppose in this case, is 20%, below which we don't consider this disease to be a leading diagnosis, so we don't perform a diagnostic test. For example, 30-year-old male patient with fever, cough, and right-sided pleuritic chest pain will not need investigation for acute coronary syndrome. At other extremes, we have pretest probability range in which we can start treatment even before a test is performed. Like in this case, it's 80%. For example, in presence of neck stiffness, fever, and skin rash, we can start antibiotics before diagnosis is confirmed. In most cases, however, we need to perform tests to establish a diagnosis. Testing and treatment thresholds differ in different diseases and depend on severity of condition and side effects of treatment. Now let's discuss about second component of formula, and that is likelihood ratios. We know test result in disease can be positive or negative. Likelihood ratios tells us to what extent positive or negative test result affects pretest probability. Likelihood ratios are calculated based on sensitivity and specificity of test. Likelihood ratio is actually ratio of two likelihoods. That is likelihood of test result in person with disease to likelihood of test result in person who is healthy. In this diagram, we have a diagnostic test that has sensitivity of 80% and specificity of 90%. If result of this test is positive, we can calculate the positive likelihood ratio by dividing positive results in disease by positive results in healthy. That will be equal to true positive results divided by false positive results. In this case, it will be 8. So positive likelihood ratio of this test is 8. This means with this test, positive result is 8 times more likely to be found in person with disease. Similarly, if test result is negative, we can calculate negative likelihood ratio by dividing negative results in disease by negative results in healthy. That will be equal to false negative results divided by true negative results. And in this case, we can see that negative likelihood ratio is 0.2, or 2:9, or 1:4.5. This means with this test, negative test result is 4.5 times more likely to be found in person who is healthy. Our negative result is 4.5 times less likely to be found in person who has disease. Formula for likelihood ratios is usually mentioned with sensitivity and specificity of test. We can see in this case sensitivity of test is 80%. So 1 minus sensitivity will be 100 minus 80, and that will be equal to false negative result rates. Similarly, specificity of test is 90%, and 1 minus specificity will be equal to 100 minus 90, and that will be equal to false positive results. We can see in this case positive likelihood ratio is 8, while negative likelihood ratio is 0.2. In this case, positive likelihood ratio of 8 will result in 8-fold increase in pretest odds, while negative likelihood ratio of around 0.2 will result in 4.5-fold decrease in pretest odds. Now we have discussed about pretest probability and likelihood ratios. Let's see how to calculate post-test probability. We know formula for calculation of post-test probability is pretest odds multiplied by likelihood ratios, and that gives us post-test odds. So first we have to convert pretest probability to pretest odds. For that we need to know difference in probability and odds. Probability that an event will occur is estimated in fraction or percentage. Suppose probability that an event will occur is 60% or 0.6. So probability that same event will not occur will be 1 minus probability, or 0.4. On the other hand, odds is probability that an event will occur divided by probability that event will not occur. Formula for calculation of odds is probability divided by 1 minus probability. So in case of probability of 0.6, we can see that odds of event are 1.5. We can use this formula to calculate pretest odds. Suppose we have pretest probability of 0.6, and we can see that pretest odds in this case will be 1.5. We already have calculated likelihood ratio of positive and negative test. We can use these values to calculate post-test odds. In case of positive results, we can see that post-test odds will be 12. That is 8-fold increase in pretest odds. Similarly, we can calculate post-test odds for negative test, and in this case it will be 0.3. Now in final step, we'll convert post-test odds to post-test probability. Formula for that is odds divided by 1 plus odds. We can see in case of positive test results, post-test odds of 12 will give us post-test probability of 92%, while in case of negative test results, post-test probability will be 24%. So we can see for this test, if result is positive, the post-test probability will increase from 60% to 92%, while if result of this test is negative, post-test probability will decrease to 24%. If we know pretest probability of disease and likelihood ratios, we can determine post-test probability without any further calculations with help of a normogram. Suppose we have pretest probability of disease of 0.5 and likelihood ratio of positive test 10. We need to draw a line from pretest probability to likelihood ratio. Then a straight line from here to third column will tell us the post-test probability of disease, like around 91% in this case. In our example, we had pretest probability of 0.6 and likelihood ratio of positive test was 8, and we calculated post-test probability was around 92%. So we can see we can find this post-test probability with help of normogram without performing calculations. Similarly, for negative test, our post-test probability was 24%, and we can see it with the help of normogram. We can find the post-test probability without performing calculations. Now we can see although our post-test probability for negative test is 24%, it's still above the treatment threshold of 20%, and we may still start the treatment. So we can see that a negative test helps us in ruling out disease if it results in significant decrease in post-test probability, while a positive test helps us in confirmation of diagnosis. If likelihood ratio is 1, it will not result in any significant change in post-test probability. So suppose if the pretest probability is 95, it will give us the post-test probability of 95 as well. Treatment threshold on scale of post-test probability depends on nature of condition and adverse effects of treatment. In this table, we can see how different values of positive and negative likelihood ratios result in approximate change in post-test probability, even without using normogram. In summary, we have discussed how to calculate post-test probability by likelihood ratios and how to find post-test probability with help of normogram. We calculated post-test probability with likelihood ratio of one test. However, we can combine likelihood ratios of more than one test to calculate post-test probability as well. If result of a test is in continuous values, likelihood ratios of subsets of result can also be calculated if sensitivity and specificity values are available.